All right, ladies and gentlemen, let's go ahead. Let's talk pressure. Now, we've talked a lot about K and T, the kinetic molecular theory, how particles start to interact. They have this attraction. If they have no attraction, they're a gas. If they have no attraction, then they're a gas. They're moving in continuous rapid random motion. And as they're moving, they hit, they collide, they bounce, they collide, they collide, they bounce, they collide. And these collisions create a force. And this force over a given area gives us pressure. Now, we've talked about a couple of different ways that we can change pressure. We could change temperature. If temperature goes up, particles move faster, they collide more often, pressure goes up. We could change the volume. We could put them in a bigger box. In a bigger box, if we increase the volume, the pressure will decrease. Okay? Now, there was one other way we could change the pressure that we haven't quite got a formula for. We've got a formula for pressure and volume. We've got a formula for pressure, volume, and temperature. We've got these formulas already taken care of. But there's this new way that we can change the pressure, and that's by changing the number of particles in our container. If we have fewer particles in our box, they're going to collide less often. They collide less often, we got less pressure. So this is a relationship we need to look into a little bit. Now, we know in the lab we can measure pressure using a barometer. We can measure the volume either by water displacement or by measuring the amount of space it occupies, length times width times height. We can also measure the temperature, the kinetic energy, using a thermometer. We can measure all these things. We can also measure the number of particles, or the moles. So we take all these pieces, we measure them, and we look for a relationship. We calculate a formula, if you will. Now here's the good news. This has already been done for you. This relationship between pressure, temperature, volume, and the number of moles is what we call the ideal gas law. Oh, it is the end-all, be-all, all variables, one formula, awesome money formula. It is the mathematical relationship between the number of the pressure, the volume, the temperature, and the number of moles. All of these values, all of these different mathematical factors together into one formula. We can reduce this back down by keeping the correct things constant, by holding different variables constant. We can reduce this back to Boyle's, back to Charles, back to Gay-Lussac's, which you don't need to know, back to Avogadro's law, by holding these different variables constant. Okay? So, I know you're dying. You're on the edge of your seat. You're going, Mr. Jorgensen, what is the ideal gas law? Well, ladies and gentlemen, repeat after me. Pivnert. Let me say that a little clearer. Pivnert. I'm saying it a little higher. Pivnert. Just that you can hear it and it starts registering. It just gets kind of stuck up there. Pivnert. Repeat after me. Pivnert. 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 PV equals nRT. PV equals nRT. P is for pressure in atmospheres. V is for volume in liters. N is for the number of moles. R is a universal gas constant. This is a constant, just like the speed of light. It never, ever, 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 ever changes. It is the same forever. It is just a mathematical number. And we're going to use, most often, we're going to use this first one, this 0.08206 liters atmospheres per mole Kelvin. This is the one we're going to use. Okay? Now here's the good news. You don't have to memorize that. I will always provide that for you. Okay? That's good news. Okay? It is a mathematical constant. It is really a mathematical fudge factor. This is universal gas law constant. This is universal gas constant that lets this formula work. Without it, it's broken. It doesn't work. And T is temperature in Kelvin. Now, in our other gas laws, we said volume could be milliliters or centimeters cubed or liters, so long as it was the same on both sides. We're okay. Not anymore. For the ideal gas law, it does not work unless you have atmospheres, liters, moles, and Kelvin. It's got to be those units. It's got to be. Because if not, it doesn't work. Cool, let's try one. Okay, so let's say we want to know what temperature 2.10 moles of nitrogen gas would occupy if it has a pressure of 1.25 atmospheres in a 25.0 liter tank. Well, let's just go through and let's think for a second here. We've got moles in our gas law formula. That was our N. We've got atmospheres. Atmospheres measures the pressure. Liters measures the volume. We are looking for the temperature, so that is our variable. Remember that your gas law formula is PV equals nRT. Well, let's plug in our pieces. We know our pressure is 1.25 atmospheres. We know that our volume is 25.0 liters. Pressure times volume equals the number of moles, which in this case was 2.10 moles, times R, which was 0.08206 liters atmospheres per mole Kelvin. I'm going to run out of room just a little bit. Hang in there. And we got temperature. And we said temperature, and I'm just going to squeeze it down there because I'm running out of space, is our X. All right, so we got all the pieces. Let's go ahead and solve. Now, before we really start number crunching, check out what happens. Remember that mathematical fudge factor, the magic number? Here's why it's so magic. We have liters on the left side of our formula. We have liters on the right side. Left side and right side cancel each other out. We have atmospheres on the left side, atmospheres on the right side. They cancel each other out. On the right-hand side of our formula, we have moles on top and moles on bottom. They cancel each other out. The only unit that did not cancel from our magic number, that universal gas constant, is Kelvin, the unit for temperature. That's what we're trying to solve for, folks. We've got ourselves a formula. Let's go ahead and work this out. So let's go ahead and start. We got two numbers on the left-hand side. We'll just multiply them together. When we do that, we get 31.25. That's going to equal 2.10 times 0.08206 times x. Well, when you do that, you get a value that is 0.172326 x. X comes along for the ride. Well, this just became an algebra problem, didn't it? The chemistry part has kind of flown away a little bit. All we've got left is to solve for x. Well, we've got a number times x right now, so to get x by itself, we're going to divide both sides by that number being multiplied to x. 326. What you do to one side, you must do to the other. We cancel from the right side, so now x is going to equal, when you divide those out, you get 181. The only unit that didn't cancel was that Kelvin, which is our unit for temperature. Now, note, this doesn't work unless these units cancel out. If you had atmospheres on the right and millimeters of mercury on the left, we're going to have a problem. So you got to get those units. Now, there's a couple different units I can give you for pressure. I can give you atmospheres, millimeters of mercury, torr, pascals. Don't let that stop you. You know how to change those. Change them to what you need, plug it in. I can give you something other than liters. I can give you milliliters. Well, milliliters divide by 1,000, boom, in liters. I can give you centimeters cubed. All right. 1 centimeter cubed is 1 milliliter. So if you had 50 centimeters cubed, you'd have 50 milliliters. Then you just have to either divide by 1,000 or move your decimal to change it into liters. What can I give you instead of moles? I could give you grams. If I gave you grams, you should probably just quit, be done. Because there's no way there's no tool we know that change grams to moles. Can't do it. Grams to moles, moles, mass, molar mass. That's the one. Molar mass, grams into moles. Get your moles, plug it in, off you go. And instead of Kelvin, I guess if I really want to be mean, I can give you Celsius, but all we'd have to do is add 273. Cool. Don't let the units stop you. You know how to change those units to get into what you want, to get into what you need. Okay? But please note, for the ideal gas law, pivot, you have to be in these specific units to let that R work. Cool. You try some for me.